Hello students, today we are going to explore more aqueous chemistry of cobalt 2+. I'm sure you have remembered the very nice red hexaaquacobalt 2 complex you have encountered in practical 16. I think that is FA1 over here. So this is actually cobalt 2 carbonate. Yeah, so we're going to explore a little bit more today. And I guess it will also help you in your transition metal chemistry. Yep. So if you recall what we did for cobalt carbonate, we actually added one spatula full of cobalt carbonate, and then we added hydrochloric acid. And then after filtering, you get this red solution. Yeah, I prepared earlier on. So this is the red solution. I'm not going to waste time preparing it for you like what we did in the review for practical 16. Okay, then today we're going to do something different. We are going to add concentrated hydrochloric acid. So we're going to observe what's going to happen. Okay, so first of all, without further ado, this is concentrated hydrochloric acid. I think so it's about 37%. So for safety's sake, I wore gloves and I'm just holding it using the test tube rack. So I'm going to introduce some concentrated hydrochloric acid over here. Okay, so just going to introduce quite a bit. Okay, yep, I think that should be more than enough. Okay, then now I'm going to add cobalt carbonate, which is over here. Okay, very carefully going to add some amount of cobalt carbonate. Okay, I want you to take notes of the difference in the color. Okay, yep. Going to add a little bit more. Okay, at the same time, just a little bit more as well. Okay. I want you to take note of the difference in the color. It's a very nice, looks like turquoise. Okay. Bit of turquoise, but it's actually blue in color. So you are forming a slightly different complex. I'm just going to add a little bit more concentrated hydrochloric acid. Okay. Okay, I'm going to swirl. I'm not going to heat it. It's going to be a little bit dangerous, but this should be enough. Okay. After I swirl, I'm going to do a filtering. Okay. Similar to what we did earlier on. Okay, so I'm going to do a filtering over here. Take note of the difference in the observation. Okay, do you see the blue color solution? Okay. Okay, so I'm going to just remove it. Okay, going to just wash this. Okay, I want to do a little bit of explanation. What are we actually getting to? So we are actually getting this particular complex, COCl4 2-. So this is the complex we are getting. This is what we call tetrachlorocobaltate 2 complex. Okay, so this is the complex we are getting because in concentrated hydrochloric acid, we have a lot of excess chloride, which will coordinate to the cobalt 2 center. Okay, so right now, I'm just going to take a brief look. You can see that getting a very nice blue color here. Okay. I'm just going to leave it here for a while. Okay, just going to leave it here for a while. Going to move on to working with the usual hexaaquacobalt chemistry. Okay, so later on, I'm just going to show you some ligand exchange experiment, which I hope you get interested in. But before that, I'm just going to bore you with some chemistry which you have already observed earlier on. Okay, now I think the first thing I'm going to do is I'm going to add sodium hydroxide. Okay. I'm going to take some ice cubes. Okay. I'm going to take a little bit of cobalt 2+ from here. Okay. I'm just going to put it in. The reason why I'm going to put it in over here, right, is because I don't want the formation of the pink cobalt 2 hydroxide to occur so quickly. Okay. I just want to show you a very nice blue. Okay. So it's the same thing. I'm just going to wipe clean so that you can observe it. This is sodium hydroxide. Okay, so I'm just going to add. You can see the formation of the blue PPT. Go a little bit. It's a very nice blue PPT being formed. I'm just going to add a little bit more. Yep. Hope you can see for now. Okay. Just going to adjust it here. Okay. So this is a very nice cobalt 2 hydroxide PPT. Okay, which is what we are expecting in our usual observation. Okay, so this is a very nice cobalt 2 PPT. And as you have predicted, if I'm going to heat it, okay, I'm just going to turn on the flame. Okay, I'm just going to heat it over here. Okay, please observe. Can you see the transformation? Okay, it's now pink. Okay, I'm going to switch off the flame. Okay, this is the pink PPT, cobalt 2+, cobalt 2 hydroxide. I'm just going to cool it a little bit in this ice bath. Right, now I'm going to show you another aqueous chemistry. Instead of adding instead of adding sodium hydroxide, I'm going to add aqueous ammonia. Yeah, so you'll be surprised what you're going to observe. Quite interesting. Okay, again, I'm just going to cool it for a while. Cooling actually helps quite a bit. And aqueous ammonia, we use aqueous ammonia. Okay. Take note what you're going to observe. Whether you can observe the pale blue PPT, which is cobalt 2 hydroxide. You notice that you don't really observe any precipitation. That's something for you to think about as well. And you don't observe any precipitation. However, right, you notice that the solution becomes a little bit brownish. Okay, gonna add a bit more. Maybe very slight blue precipitation. Yeah, but you don't really get to observe it. But what you observe at the end of the day, right? Okay, so now you do observe a little bit of PPT coming out. Okay. Yes. Yes, it's now out. Okay. This is the blue PPT. Okay. Just going to swirl it. Okay, the blue precipitates. Okay. Now, after that, I'm going to add excess aqueous ammonia. Please observe what's going to happen. Okay, I'm going to stir it. Hmm. Gonna wait for a while. Okay. Then I'm going to come back to it later. Now, this is the pink solid. Okay. It's now quite cold. What we're going to do now is I'm going to add hydrogen peroxide. Okay, so please observe what will happen. You notice a lot of bubbling. Okay, so likely to be the production of oxygen gas. Okay, take note of what happened to the solution and what you're observing. Okay. Okay, we'll come back to it later. Okay, the bubbling is still there. Now I'm going to return to this solution. Okay, so you can sort of observe that in excess ammonia, right, the PPT kind of dissolved to give you this colored solution. I'm just going to pour some of it out because I think I've added a little bit too much. Okay, I'm just going to pour some of it out here. So pardon me for that. Okay, I'm going to pour some of it out. Okay, I'm going to add a little bit more aqueous ammonia so that you can observe the complex being formed. Okay, so this complex being formed, oh, like, is it brown in color? It's a little bit brown. Okay, so this complex is actually hexaaminecobalt cobalt 2 complex. Okay, so I'm going to write it on the board. So this is the hexaaminecobalt cobalt 2 complex, which looks like this. Okay, so this is the complex that's formed. Okay, how does it form from cobalt 2 hydroxide? Okay, so it's formed from cobalt 2 hydroxide because cobalt 2 hydroxide is able to maintain a small amount of cobalt 2 plus and OH minus by virtue of its KSP. Yeah. However, we can also view this as hexaaquacobalt 2. So this particular hexaaquacobalt 2, right, you will undergo ligand exchange experiment. And in the process, 6 of the ammonia ligand, right, will then displace the H2O ligand to give us hexaaminecobalt 2 complex. and in the process, the 6H2O ligands come off. Yeah. So this is pretty much similar to the copper chemistry, which you are familiar with. Okay, I think it's yeah, it's over here. Okay. Now, what is interesting is that if I'm going to introduce H2O2, similar to what we did just now, and you see this earlier on, this is the cobalt 2 hydroxide. Now it turns like a bit brownish. If you add a bit more, I don't know what's going to happen. I think more reaction is taking place, so I'm just going to wait for a while more. This is the original cobalt 2 hydroxide. Okay, but for this hexaaminecobalt 2 complex, what's going to happen is this. Please watch. Look at what happened on the surface. Okay, the color darkens, right? Yeah. So you expect some form of redox taking place. Okay. So what exactly happened? Okay. So what exactly happened here is that we are getting hexaaminecobalt 3 complex. Okay, you can tell. Okay. So now it may be a little bit early for most of you who are doing transition metal, or we are not doing transition metal yet. You may feel a bit confusing, but not to worry. When you are working on your transition metal, you can always come back and revisit this particular video so that you can understand things a little bit better. And then, of course, the difference is this one doesn't give up. Does it give off oxygen? Yes, it does. You can observe the bubbling here. Okay, so maybe we can test for the oxygen. Shall we do that? Okay, so I'm going to shift this for a while. Let us try to test for the oxygen. Huh? Okay. Is it obvious that there's oxygen? We'll try again. We want it to burst into flame is going to be quite tough. Okay, I think this is good enough. Okay, so what does this tell you? Redox takes place. What about this? Okay, you can try as well. It's good to try. Okay, I think this is obvious. Okay. Right. Okay, I think I have explained quite a bit of the chemistry to you, right? So now let us go back to our interesting tetrachlorocomplex. So this is the blue okay one. So I'm going to just put it at the side. This is a very nice tetrachloro. Okay. Going to erase the board. The first thing we're going to do is, okay, we'll try to understand what happens when we add H2O. Okay, so what I'm going to do is I'm going to put in some deionized water over here. Okay, then I'm going to use a clean dropper to introduce okay, take note of what happens. What do you think happens? It gives you a very familiar pink. Do you notice? Okay, so this very familiar pink is something which we'll be discussing. Okay, so I'm going to just use this particular solution. It feels a bit warm because of dilution. Okay, remember that earlier on what we have is concentrated hydrochloric acid. Okay, so why does this happen? Okay, so we'll do some board work. Okay, so I'm sure you know that what we are getting here is probably hexaaquacobalt 2 complex, and in the process I have 4 chloride ligand coming out. Okay, but why is it that when we add water, we get a pink complex, which is over here? Why is that the case? Can we say that the addition of water will cause the position of electron to shift to the right? Actually, this is not a correct thing to say if you remember what we did in JC1, because water is actually part of the solvent. So you cannot say that according to the Chatelier's principle, the position of equilibrium will shift in a position in a direction so as to reduce the amount of water added, but the concentration of water is fixed at 55.6 moles per dm cubed. So we cannot be using that to explain. Better way to explain is to use what we call reaction quotient. Okay, so how are we going to go about explaining that? Okay, so first of all, right, we need to understand how can we write out our Kc expression. So in our case here, the Kc is actually the concentration of the hexaaquacobalt 2 complex. Okay, 2 plus. Okay, multiply by Cl minus. Okay, divide by the tetrachlorocobaltate complex. Okay, and that's about it. Okay, if we're going to take out the volume term, so this is an equilibrium expression, so we can actually take out the volume term. So when we take out the volume term, right, what we're going to end up with is that we're going to end up with the number of moles of hexaaquacobalt 2 complex at equilibrium, multiplied by the number of moles of chloride to the power of 4, divide by the number of moles of tetrachlorocobaltate 2 complex. Okay, and then of course here we multiply by 1 over v to the power of 5, divide by 1 over v. Okay, remember that we take out the volume term. Okay, and then when you combine the two, right, eventually you cancel, then you're going to end up with this whole thing multiplied by 1 over v to the power of 4. Yeah, so that means that when water is added, what's going to happen is that my QC, right, will become less than Kc. Yeah. Why is that the case? Because when water is added, the volume term gets bumped up. Everything else stays the same. So QC is less than Kc. In order to restore equilibrium, means in order for the value of QC to go back to the Kc value, yeah, the position of equilibrium needs to shift in the direction so as to increase the value of the denominator. Okay, so in this case, maybe not concentration here. So increase the value of the denominator. Numerator, and decrease the value of the denominator. So the effect is that the position of equilibrium shift to the right. So what you observe is this very nice pink complex. okay, which is hexaaquacobalt. Okay, I hope this explanation makes a little bit of sense to you, because this is indeed what you observe when you are actually dealing with the chemistry, and you have seen it with your own eyes. There's no tricks involved. What I did was I took out this, okay. I took out this, I put it into deionized water, and this is what you end up with. Okay, so now let's try something interesting. Okay, shall we? Let's try something interesting. What happens if we add in calcium chloride? Okay, calcium chloride is a source of chloride. I mean, it's pretty obvious to you what we are solid here. Okay, so when I add it in without swirling, okay, without swirling, I want you to observe the bottom. Okay, let's try. Okay, so I'm going to add in calcium chloride. I'm just going to pour it in, although this is not a very good way of delivering the. Okay, I'm just going to pour it in. I want you to take note of the bottom. The bottom layer. Do you see the blue hues? So that is the tetrachlorocobaltate complex. Okay, I'm just going to add more. Okay, just trying to add more so that hopefully. Now, can you see that? Okay, can you see the side? Okay, so indeed, the addition of chloride pushed the position equilibrium back. Okay, back to the tetrachlorocobaltate complex. I'm going to swirl this. I want you to tell me what is the final color you're getting. Okay. We're going to get this very nice blue complex. Okay. Probably I'm going to add a little bit of deionized water. And then what happens? Can you see the very nice two layer without swirling? Yeah, so the top happens when the reaction quotient exceeds, is less than the Kc, and position equivalent now shift to the right, okay? But if I saw it, I think you're probably going to predict that you're going to end up with purple, because it's a mixture of blue and pink. Let's see if this is indeed the case. Okay, can you see? We're going to end up with purple. Yes. Okay, very close to purple in color. More of lilac rather than purple. Okay, so this is what you are expecting. Okay, yeah. Okay, so I hope you get to see that. Oh, you know, like when I added in the chloride artificially from calcium chloride, you can see that surrounding the bottom and then nearby the part of the solution touching the solid chloride, you actually observe the blue tetrachlorocobaltate 2 complex. Okay, and then after that, I add in the deionized water, and then you see half-half, because the top it's now majority hexaaquacobalt 2. Bottom is still the tetrachlorocobaltate 2 complex, and then I swirl it, I get a good mixture. Okay, yeah. So now I'm going to show you something quite interesting as well. Okay, with deionized water over here. Okay, I'm going to again add this tetrachlorocobaltate 2. Okay. Okay. Again, after I added in, you probably acknowledge that you get the hexaaquacobalt 2 complex again. Okay, so now I'm going to do some heating. Okay, why is that the case? Because now, okay, maybe before I heat, let me put it in ice bath. The reason why I'm doing this, okay, ice bath. The reason why I'm doing this, right? Because now I want to ascertain whether the ball reaction is exo or endothermic. Okay, yeah. So I'll have to put it into the ice bath. So you can take a look. I'm going to take the Bunsen flame here. Okay, the Bunsen flame. I'm going to switch it on. I want you to observe this very interesting demonstration. Turn down the flame a bit. Okay, now please observe. No trips. This is pink, the hexaaquacobalt 2 complex. Okay, I'm going to keep it. Please observe. In case you need the paper, show you. Do you see the color change? A bit purple now, right? Yeah. So I think you're expecting cobalt 2 tetrachlorocobaltate 2 complex to form as well. It's now very, very purple. Is this the very familiar blue color? Is it the familiar one? Okay, I'm going to switch off the flame. Okay. Just to show you the color. It's very nice blue color. Okay. Is it familiar? I hope it is. So now I'm going to put it into the ice bath. Okay, just going to wipe the side. What do you notice? The cooling results in the formation of the pink complex again. Okay, so from here, can you tell me whether the flow reaction is exo or endo? Okay, so remember that according to the Chatelier's principle, when you apply heat to the system, the position equilibrium will shift in direction so as to partially mitigate the increase in heat. Yeah. So if I apply heat, you get the blue complex. So that means that the fall reaction is exothermic. So delta H forward is less than 0. Less than 0. Okay. Yep. And then of course, when I introduce the ice bath to the system, now what happens is that the position equilibrium will shift in the direction so as to partially mitigate the reduction in temperature. So you want to generate some heat. And because of that, solution turns pink back to this complex. Okay? If you don't believe it, let's try again. Okay, let's try again. Okay. I'm going to try again. As well. Okay, can you see that it turns purple already? Okay. Okay, so now it's blue. Okay, no tricks. Okay. Try again. So already give me the purple complex. Okay. After a while, I'm going to get back the pink. Okay. In case you are wondering, does it work with what we did earlier on? Remember, we artificially added in the the calcium chloride. Yes, it works as well. So what we get is this purple color, right? I'm just going to put it into the ice bar. And you observe that the purple color now becomes a little bit more pink. Is it a little bit more pink to you? I hope it is. I'm going to heat it. Okay, because we have a greater amount of solution now, I think the effect will be a little bit more dramatic. Do you see that now it turns really, really purplish, more lilac? Okay. It's really blue now. Okay. This is quite, because the volume is too huge and solution is not concentrated. So I think the color is not so obvious, but you know where I'm coming from. Okay. So this is the blue which we were talking about. Okay. Okay. Just going to remove the heat. Okay. It's the same idea, similar idea. So you can tell that the species is the same. So again, put it into the ice bar. You can see that the bottom portion turns pink first. Yeah. Okay. So kind of like back to where we started. Okay, I hope you enjoy this particular field experiment where I try to introduce you more cobalt 2 plus chemistry. So please take a look out for future videos I'm going to create related to any aspects of chemistry. Okay, thank you very much. Have a great day.